So let us now see parameter synthesis algorithms. We saw in the previous session that most interesting problems are undecidable for parametric time automata, but we can get some decidability by adding some restrictions on the number of clocks or on the use of parameters. We now see some parameter synthesis algorithms. So first, as a side comment, all we see in this session is about parametric time automata, but you will see this afternoon that it is very close to parametric time Petri nets. So in fact, most techniques here, and including the algorithms we will see, can be redefined in a very similar manner for parametric time Petri nets. So before going to parametric time automata, let us go back a bit on time automata. So on time automata, we know that there are an infinite number of concrete states, because although we have a finite number of locations, clocks can have an infinite number of values. Clocks can be arbitrarily large, so they can go towards infinite, and they are also dense because they are real valued. So we have an infinite number of real values, including in a finite interval. So this gives two reasons for an infinite number of concrete states. However, we can group all concrete states reachable by the same sequence of discrete actions. So we can reason in a symbolic manner. And so we will consider symbolic states. A symbolic state has a discrete part, so the location, and has a continuous part. And this continuous part will encode in a finite structure an infinite number of clock valuations. So for a time automaton, this continuous symbolic part Z can be represented by a convex polyhedron with a very specific form, and we call this a zone. So the form is an integer smaller or equal to a clock, and a clock smaller or equal to another integer, and then a difference between two clocks smaller to an integer or potentially infinite sometimes. And so we can compute those successive reachable symbolic states in a symbolic manner using polyhedral operations. For instance, if we have a symbolic state Lz, so discrete part, continuous part, we want to know the successor via an edge. So an edge of a time automata is a transition from a source location L to a target location L prime via action A with guard G and resetting clocks R. Okay? And so the target symbolic state will be, as a discrete part, of course, the target of the transition, L prime, and then a long expression that I will explain in the next slide. And so if we do this with an additional technique, we can get a finite number of reachable zones. So in very brief, the additional techniques will be to also bound to abstract together some zones when we have clocks greater or equal to the highest integer constant of the system. So we can group them all together and then we get a finite abstraction. Now let us show graphically what is this long expression about. Let us consider this very small time automaton. The initial state is a green location with an invariant y smaller or equal to 4. Then I will take the transition with a guard x greater or equal to 2 resetting y and going to the blue location. Okay? In the initial location, the blue location, my clocks are both equal to 0. However, I can also perform some time elapsing. Not forever, only until the invariant gets violated. So I can perform elapsing. This is both clocks, this is the value of x, this is the value of y. And then I will do elapsing. Both clocks evolve at the same rate, but they stop here. They stop at x equal to y and x smaller or equal to 4. So this is the symbolic representation of all possible value of clocks in the initial state. And it can be written as the initial value of the clocks, time elapsing, intersected with the invariant of the green location. Now let us take the transition. This was my former symbolic state. So the first thing I will do is to consider the guard. I can only leave this state when x is greater or equal to 2. So I intersect with x greater or equal to 2, and I get this symbolic set of clock valuations. Then I will reset clock y. So I will put clock y to 0, which gives me this symbolic representation. Okay? Now my clock y is set to 0. Then I enter the blue location, and I can again let time elapse. So both clocks will evolve at the same rate. And here it's a bit easy because there is no invariant in the blue location, but if I had an invariant, I would need to intersect with the invariant. For instance, y smaller or equal to 2, I would just cut here y smaller or equal to 2. And this is how I can reason in a symbolic manner. And by doing this, I will get a finite number of such symbolic zones, and I will get a finite computation of the behaviors of my time automaton. Now for parametric time automata, it will be very similar, except that my continuous part, this polyhedron, the Z polyhedron, is not only about clocks, but also about clocks and parameters. So clock will be compared to parameters, clock will be compared to clocks, and parameters will be compared to parameters. So I get a higher dimensional polyhedron. We can extend the reset and the time elapsing to those parameters. And it was shown in 2002 that those polyhedra have a special form that we call a parametric zone. So if I take a parametric version of the former example, I will not go into detail, but just to show you, this will be the initial state. Again, both clocks are equal to each other, and then y is smaller or equal to p because of the invariant. Then, once we take this transition, the difference between x and y is greater than q and smaller than p. And we'll also have that q is smaller than p because of the previous inequality. You saw that q smaller than x minus y smaller than p implies that q must be smaller than p. So you can only go to the blue location if q is smaller or equal to p. And then, of course, all variables are non-negative. So I will not go into more details, but it's just to present to you that we have a symbolic way to compute the state space of a parametric time automaton. However, a very bad news compared to time automata is that this computation is not finite, and we know no finite abstraction. Actually, even worse, we know that there exists no finite abstraction. Why? Because if there existed a finite abstraction, we could give an answer to all those problems, the emptiness of the set of valuations, the universality of the set of valuations, and so on and so on. But since we know those problems are undecidable, it is hopeless to look for a finite abstraction of a PTA that will answer those decision problems. We know it cannot be done. Still, we can do a semi-algorithm to compute the answer to the EF problem. EF, you remember, is a reachability. So my goal will be to compute EFG, meaning G is a set of location, or just one location, if you like, and I will want to compute all valuations for which a location in G is reachable. So we have two arguments in this function. So it's written in a functional form with a recursive form. We have two arguments. S is a current symbolic state. You remember a symbolic state has a discrete part, L, and a continuous part on clocks and parameters. M is a list of visited states. It's just to avoid to visit 2 times the same state. And suc of a state and an edge will compute all the successors of a symbolic state via some edge. Actually, it's the only symbolic successor of x via this edge. So we have 3 cases in this function. When we compute EF of Sm, first we check, so S has a discrete part L, is my discrete part L into the set of goal locations that I'm looking for? If so, I finished. I found a state reaching the desired location. So I will return this expression. This expression means the projection of the symbolic zone onto the parameters. What does this mean? Let me go back on the previous slide. On the previous slide, I had here a symbolic zone with clocks and parameters. And if we project this onto the parameters, we eliminate the clock variable using variable elimination technique, and I will get exactly q smaller or equal to p. So this is a reachability condition. It is a condition under which the blue location is reachable. So I can reach the blue location if and only if q is smaller or equal to p. So if I met my goal location, my target location, I will output the projection, so the parametric reachability condition. Otherwise, if S belongs to the set M, M is the set of past states, meaning I already met the state S. I can safely stop. I already visited the state, I am along a loop, I can stop locally the analysis, so I just answer nothing. I say, okay, I found no new valuations, let's stop. Otherwise, I have not yet met my target state and I did not yet visit the current state, so I just explore further. Explore further meaning we return the union of a recursive computation of EF, and I recursively call it over all successors for all possible edges of the current state, so I explore all possible branches, and I recursively call EF with the new symbolic state, and I add to the set of states the state that I just met. So it's just a basic fixed point computation. So this algorithm was shown to be correct by Alexandra Jovanovic and co-authors. It's also complete. However, it may not terminate. Why? Because I explore symbolic states and I may have an infinite number of symbolic states. So the termination is not guaranteed. And another way to recall is that the underlying problem, the decision problem, is the set of parameter valuations empty or not, is undecidable. Still, there was some work beyond this EFSynth algorithm. So EFSynth is the most basic synthesis algorithm for parametric time automata. So it is not, so it is complete and sound, but it may not terminate in general. However, we can force termination. We can force termination thanks to a concept used again by Alexandra Jovanovic, Didier Lim, and Olivier Roux, which is the notion of integer hull. The integer hull, what is it? So if we have a polyhedron with clocks and parameters, like here in 2 dimensions, we will take all the integer points inside this polyhedron. And then we take the smallest polyhedron that contains those integer points. So we take the convex hull of all integer points of this polyhedron. And so we get the integer hull. And if we apply the integer hull at selected places of the EFSynth algorithm, it will terminate. Of course, there is no miracle, once more undecidable problem, we will lose something. We will lose the completeness. We will not find all valuations. In fact, it only works for bounded parameters. We may lose valuations, and the only guarantee we have is that we will get all the integer points. So we know we will get all integer valuations in a finite domain, and with some extensions to dense time, we can also, to dense parameters, sorry, so rational valued parameter, we can also get some rational valuations. But the guarantee is only integer points for bounded parameters. Other semi-algorithms were shown for more complex properties, and Didier Lim will tell you this afternoon about this for parametric time Petri-nets, in particular for the unavoidability synthesis. This algorithm, EFSynth, is implemented in 2 state-of-the-art tools, Imitator for parametric time automata and Romeo for parametric time Petri-nets. Let us see now another algorithm. This other algorithm is a trace preservation synthesis. So the problem we want to address is the following one. We have a real-time system modeled with a parametric time automaton. We know one valuation of the parameters, and we would like to find other valuations yielding the same untimed behavior, the same time abstract behavior. So we have one valuation, and we find a constraint usually around that valuation with the same behavior. So the trace preservation synthesis, also called inverse method in the past, works as follows. We will forbid all the behavior that does not exist for the reference valuation. And as a second part, we will require all the behaviors appearing in the reference valuation to occur. So this algorithm starts with a constraint on the parameter equal to true. So initially all the constraints are true. And then we compute a set of reachable states, a bit like in TPsynth. So we explore deeper and deeper in the symbolic state space. And then when we meet a state that is not compatible with the reference valuation, not compatible means that the symbolic part, now it's called C, but it's the same as the Z before, this part is not satisfied by the valuation. So in that case, we just negate the projection onto the parameters of the symbolic part of the state to the constraint. And then we do this until we have no incompatible states. And at the end, we also need to return the intersection of all the parametric constraints. I will show you an example. So a bit earlier today, I told you that we can model hardware components with parametric time automata. So this example is an asynchronous circuit studied by Clariso and Cortadella, two people working on hardware verification with parameters. And those components, so we have 4 of them, G1, G2, G3, G4. As you see, they are all connected into a kind of cyclic manner, okay? We have 2 input signals, D and CK, and 1 output signal, which is Q. My input signal is required to work like this, and the clock is doing just 1 clock cycle. And Q is the output, and I hope it will rise. I'm not sure. I hope so. As I told you briefly before, components in hardware, if you look at the very extremely fast scale, so more or less at the scale of nanosecond, you will see that hardware components do not change immediately when an input changes, but they change after some delay. So for instance, my gate G1, if I change input signal, the change of the output will not occur immediately, but after 7 time units. I think it's more or less nanoseconds, once more. So we have traversal delays. Here is an exact traversal delay. Here is an interval, 5, 6. Here 3, 7, and here 8 to 10. Okay? We have some timing constants in the environment. The clock cycle lasts for 15 plus 24. And then 10 time units before and 7 time units after the rise of CK, I know that D is equal to 1. So the question, for those timing delays, does the rise of Q always occur before the fall of CK? So can I guarantee that this occurs before this falls? So this is an interesting problem. I do not need parameters here. I can use time model checking without parameters. For instance, using the UPAL model checker, I can model this using time automata and answer. And the answer is yes. I'm sure Q will rise before CK falls. Okay? Now let us add timing parameters. So we replace the constants with a list of parameters. We have 12 parameters, 8 for the gates and 4 for the input signals. So the question becomes now, since I talk about trace preservation problem, which values of the parameters yield the same untimed behavior as the reference valuation? Reference valuation was the timing constants we saw in the previous slide. And so, since this reference valuation was correct, we know that Q has been rising before CK falls. We know that all the evaluations I will compute in this question will also be correct. Just an additional notion before going further. What we call a trace set is a set of all traces. So a trace is an alternating sequence of the discrete part, the location, and the discrete action. So I remove all the timing information from my runs. So here is the trace of my asynchronous circuit. The first action will be D rising. So the up arrow means a signal is rising, and the down arrow means signal is falling. So D rises, G1 falls, CK rises, G3 falls. Then we have 2 options depending on the timing values. You know, we have intervals. So we do not know with certainty what will happen first. Either Q rises, then D falls and CK falls, or D falls and then Q rises and CK falls. In both cases, you notice that my property is true. I'm interested in showing that Q rises before CK falls. This is true for both traces. So let us apply trace preservation synthesis to the flip-flop circuit. Here I present my reference valuation. So this is valuation for any of the 12 parameters I have. Here is a constraint I have here. Here is a symbolic state space. So I start with the red location and I have a constraint. For sake of simplicity, I remove the clock valuations. So it's a symbolic state space with only parameters. I need the clock valuations, I just remove them for getting a more simple slide. So if I take this transition, I get this constraint. Then I have two successors, and I will check that those successors are compatible with the reference valuation. So here I can reach a blue state if T setup is smaller than TLO. T setup is 10, TLO is 15, so this is true. And I can reach if T setup is greater to delta 1 minus, so T setup is 10 and delta 1 minus is 7. This is again true. However, for this constraint, the second inequality is not true. T setup smaller or equal to delta 1 plus. We have 10 smaller or equal to 7. This is not true. So in that case, I remove the state, and I remove by removing that inequality and adding it to the resulting constraint, and also for some reason in a backward manner to all other states computed. And I do this again and again until I reach a fixed point, and at the end I return the intersection of all the parameter constraints I found, which is depicted here. So what does this constraint mean? For any possible timing valuation that satisfies this big constraint, I can guarantee that the behavior will be the same as for the original system in terms of action and locations. So not about time, but about sequence of actions and location. And since my reference valuation was correct, any valuation here is also correct. This also gives a measure of robustness in terms of small variations of my timing delays. I can do any variation of the timing delays here without changing the functional behavior of the system as long as they stay in this constraint. So I really characterize the robustness of my system. Before concluding this session, a few words about software supporting parametric time automata. So the first software was high-tech, designed by Hensinger in the mid-90s. And it was actually more powerful than parametric time automata because it was a model checker for hybrid automata with parameters. Hybrid automata are a larger class than time automata. Then Favor and a bunch of other software on hybrid systems designed by Goran Fraser also support larger classes than time automata. Romeo is active since mid-2000s and is working on parametric time Petrunet with also a translation from time automata, if I am not mistaken. And Imitator is a tool that I also designed and is working on parametric time automata, and we will work on it later today. To conclude this session, we saw two algorithms. One to synthesize valuations reaching a given location, and another one to synthesize valuations having the same trace set as a given valuation, giving also a measure of robustness. There are many other algorithms for parametric time automata. Two of them in particular are the unavoidability synthesis that you will see, I think, this afternoon, and that is implemented in Romeo, and the behavioral cartography, which tries to find all possible set of valuations for which the behavior is the same inside one set of valuation. However, all these algorithms are very costly, and so we will try to improve the performances using distributed algorithm, which will be the object of the next sequence.